Hello, class. What we have to talk about today is a rule that helps us remember how many bonds atoms can form. And we're going to look at the atoms that are most prevalent in organic chemistry. And the rule is called the HONK. HONK 1, 2, 3, 4 rule. The HONK 1, 2, 3, 4 rule is H stands for halogens. So those are just fluorine, chlorine, bromine, and iodine, and hydrogens. So that's what the H stands for in the HONK. And then that H corresponds to the 1. And that tells us one bond. So we could have examples like carbon hydrogen. You can see that hydrogen only has one bond. When we look at halogens, you can see that there's one bond. But with halogens, what do we see? We see three lone pairs, 1, 2, 3 around that halogen. Why is that? Remember the octet rule, which is simply telling us that for this atom here, there needs to be 8 electrons around it. So if I look at an example like this, let's look at this methyl bromide here. When we take a look at the halogen, we see that there's 3 lone pairs, but how many electrons does it need? Well, it needs to have an octet. And that single bond that I had drawn right here, that is a sigma bond. And that sigma bond is represented by those 2 electrons there. So when we look at, and not only is this a sigma bond, it's a covalent bond. And covalent bonds share electrons. And so it shares all those electrons. So when you look at that pink circle that I drew, how many electrons are in that circle? There's 8. And so we have the octet rule is satisfied. But when we take a look at carbon-hydrogen bonds, or anything bonded to hydrogen, it's a little different in the fact that hydrogen can only have 2 electrons. And so you can see that hydrogen right there only has 2. Because it only has a 1s orbital. That's all it has. And in the 1s, you can only have 2 electrons. Okay. So that is the H. Any guesses on what O stands for? Anybody thinking oxygen? That would be correct if that's what you're thinking. So the O in the HONK rule stands for oxygen. All right. And then O corresponds to 2, so that means that there's 2 bonds. So we could have oxygen atoms that look like this. Now, how many lone pairs does it have? It has 2 lone pairs. Why? Because the HONK rule states that oxygen atoms forms 2 bonds. There's our 2 bonds. But it also needs to fulfill the octet rule. So 2, 4, 6, 8. So that's a valid structure. We can also have an oxygen atom that looks like this, a double bond to that oxygen atom. And just like that. So for example, we could draw, let's say, a ketone. What if we drew a ketone that looks like this? Okay, there's a ketone. That oxygen atom has 2 bonds and 2 lone pairs because we want to have the octet rule. You can see that if you circle that, there's going to be 8 electrons. The next one, nitrogen. In nitrogen, how many bonds do you think nitrogen holds? Well, the HONK rule tells us that it's 3. So 3 bonds. So we would see a nitrogen species that looks like this. We could do boom, boom. We could have 3 carbons attached to it, 3 bonds. But is that molecule fulfilling the octet rule? When I count how many electrons are here, I only count 6. It has to have 8. So that means there has to be a lone pair. So that nitrogen right there fulfills octet, has 3 bonds. What if I had a nitrogen atom that looked like this? What about that? That's 3 bonds, 1, 2, 3. So it has to have a lone pair. What if I had a nitrogen that had a triple bond attached to it? Let's go like that. What if we had a molecule that looked like that? We're focusing on the nitrogen. It has 3 bonds. That's what the HONK rule says. But how many lone pairs? Well, there's 6 electrons here. Has to have 8. So it has 1 lone pair. And then the last one in the HONK rule is carbon. Very, very important, because organic chemistry is all about carbons. Forming carbon-carbon bonds, using carbons to change functional groups. Organic chemistry is all about the carbon. So C stands for carbon. And in the HONK rule it says it has to have 4 bonds. So you could have a carbon with 4 bonds. Now how many lone pairs does the carbon have? Well, let's think here. Each bond right here represents 2 electrons, right? So there's 8 electrons around it. So it fulfills the octet. That's good. That's done. There's no lone pairs. What if we had a carbon with a double bond? Right there, what do we have? This carbon has a double bond. And we'll make it look like a real molecule here. I'm focusing on this carbon right here. 1, 2, 3, 4, 5, 6, 7, 8. No lone pairs. What if we had a carbon with a triple bond? So I'm focusing on this carbon right here. Okay, and we could draw another methyl coming off of that. So this carbon right here, how many bonds does it have? 1, 2, 3, 4. That means it has 8 electrons around it, so no lone pairs. Okay. What if we had a carbon that looked like this? I'm looking at this carbon in the center. How many bonds does that carbon have? Carbon has 1, 2, 3, 4. Does it have any lone pairs? No. If you did take any one of these molecules here and put a lone pair, let's look at this one right here. If I did put a lone pair there, what mistake did I make? We'll just count the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I violated the octet rule. The octet rule says 8. I have 10. That's not possible. Not possible. So that would be incorrect. No lone pairs on the carbons. Now this is very important to know and remember that this HONK rule only works when the molecules are neutral. They have to be neutral in order for this molecule, for this HONK rule to work. The moment you make these molecules have a formal charge, like a plus charge, or you could draw a molecule with a negative charge, the HONK rule does not apply. That is very, very important to remember when you're using the HONK rule. Only when the molecule is neutral does this work. So that leads us into carbons that have charges with them. So let's erase this HONK rules and look at carbon atoms with charges on them. So before we start looking at the charges, what if I drew a molecule that looked like that? How many carbons would you say you have here? Hopefully you're all saying that there are 4 carbons. How many hydrogens? 3, 6, 9, and 1 coming off here. So H10. Now when we take a look at this carbon in the center, do you see how it has 4 bonds? It's following the HONK rule. So if I draw it out, we would have it look like this. CH3, CH3, and then a hydrogen coming off. That follows the HONK rule, right? Because it has 4 bonds. But what if I take that same molecule here, like this, and I draw a positive charge? And when we have a positive charge on a carbon atom, we call that a carbocation. Now, carbocations are telling us, hey, we have a positive charge here. And so that positive charge is telling us that we are missing one of the 4 bonds. And so when we look at this carbon, we see that we have 3 bonds. So what bond is missing? Well, it's going to be this hydrogen atom that's missing. So this carbocation has a chemical formula of C4H9 because it's missing that hydrogen here. Now, there are different types of carbocations. This carbocation is a tertiary carbocation. And tertiary carbocations are this positive charge, or this formal charge, is attached to this center carbon. And whenever I draw a formal charge, I want you to, I circle it. So if it's a positive 1, a positive 2, negative 1, negative 2, it doesn't matter what the charge is, I circle it. And that's going to tell me and you that that is a formal charge. And so we'll know what we're talking about. So that is a tertiary carbocation, because when you look at that central carbon that the formal charge is attached to, you can count that it has 1, 2, 3 carbons directly attached to that center carbon. So that is a tertiary carbocation. Now, if I drew a structure like this and placed a positive charge on that right there, when I'm looking at this carbon right here, it's telling me it has a positive charge. And the HONK rule says if it's neutral, the carbon would have 4 bonds. But because it's positively charged, it's telling me I'm missing one of those 4. And so what we have is we are missing one of the carbon-hydrogen bonds. So I'm going to actually take this positive charge here and draw it below. And let's just contrast it real quick with the neutral. If we are looking at this carbon right here, how many hydrogens does this carbon have? Well, it has 2 hydrogens right there, because this carbon right there in the center needs 4 bonds, right? But we have a carbocation now, and so we're going to lose one of these, so now we only have one of those hydrogens. And so this carbon right there has how many bonds? 1, 2, 3. So another way that you can look at it, if a carbon atom has 3 bonds, it's going to be +1. Now, this is a formal charge. Do you remember calculating formal charges in general chemistry? If you don't, highly recommend going back and learning that. We will talk about it and I'll help refresh your memory, but it's better that you go back and learn it and make sure you understand it, because you learned it before, okay? But I will help you remind yourselves. So now when we take a look at this carbon, or this carbocation, what degree of carbocation is it? Is it a tertiary? Well, when we look at that central carbon, how many carbons are directly attached to it? There's 1, 2. So that makes this carbocation a secondary carbocation. And I'm not going to spell out the whole carbocation. Now, we could draw another molecule and draw a positive charge for that carbon there. Let's contrast it to a neutral one. So this carbon right here, we can see that there's 1 carbon-carbon bond, but then it has 3 carbon-hydrogen bonds that are not shown. So that's the neutral form. Oh, but this guy's positively charged. So that means it can only have 3 bonds. So we could see 1, and let's move this positive charge here out of the way for a moment. Let's put it right there. Do you see how there's 3 hydrogens? Now there's only 2. Okay. So when I redraw this without the hydrogens, it looks like this. So these 2 molecules right here are the exact same. Now we see that there's this central, or this carbon here. That's what the positive charge is attached to. How many carbon atoms are directly attached to that guy right there? It's just that guy, only 1. So that makes this right here a primary carbocation. And it's very important that you're able to see that, the different degrees of carbocations, because in the future, depending on the carbocation, it will determine what type of reaction it can undergo. So understanding and being able to identify the degrees of these carbocations will help you understand reactivity and be able to predict reactivity. That's the skill set that you want to have in organic chemistry, because you cannot memorize all the reactions that we are going to go through. You need to understand the principles that I'm teaching you here, and this is one of those very important principles, looking at the degree of the carbocation. So we've taken a look at carbocations. Well, we can also have something called a carbanion. So if we look at the same molecule that we've looked at before, we'll keep that neutral. So the HONK rule says that there's going to be a hydrogen here. We just looked at if we have a positive charge, that means the hydrogen is missing, and that's a carbocation. But what if we had a lone pair and a negative charge? That right there is called a carbanion. Or sometimes we just say it really fast and say carbanion. What we have here now is, when we take a look at this central carbon, let's draw it out like this. Boom, boom. When I take a look at that central carbon, how many electrons are around that central atom? Well, there's 2 here, 2 there, 2 there. So that's 6, 7, 8. So that central carbon there has 8 electrons in it. So it has fulfilled the octet. But here's my question to you. Do you think that there is still this hydrogen, is it on the carbanion? What do you think? Well, think about it and just draw it out. Now, if I have the hydrogen there, how many electrons are around the central carbon? 2, 4, 6, 8, 9, 10. That violates the octet rule. So that guy, it doesn't work. There's too many electrons. So what we have here is a carbanion. It is missing that hydrogen. But it does have a lone pair. So when we take a look at these 3 different anions, that's not correct because they're not all anions, is that? These 3 different structures here, we have a neutral carbon, a positive carbon, and a negative carbon. How do I know this is a +1 and that's a -1? Back to the idea of calculating formal charges. Now, if you go back to general chemistry and review your notes, your instructors would have taught you how to do it their way. And a textbook would teach you how to calculate formal charges. You could go on YouTube and they have ways to do it also. I have my way of doing it and I hope it works for you, but if not, find a way that works for you. So what we're going to do is we are going to look at just these central carbons and calculate the formal charge on each one of those. And the formal charge has to match what we have here. So the first thing that you do here is you need to go to your periodic table and find out how many valence electrons the atoms have. And let's see, I'm going to grab my book here. So I have my textbook right here, and I'm just looking at a periodic table. And when you look at your periodic table, you see that the elements have different groups. And those groups are the vertical columns. Okay? And when you look at those vertical columns, carbon has a number of 14 above it, and nitrogen has a number of 15, oxygen has 16, and fluorine has 17. So it looks like this. So carbon, nitrogen, oxygen, fluorine. And it has a group number of 14, 15, 16, 17. When I look at that, I'm only paying attention to this last digit here. And that number in that last digit, 4, 5, 6, 7, is telling me how many valence electrons that element has in its neutral state. That's the trick. These numbers here tell us how many valence electrons an atom has in its neutral state. So when I look at this molecule, I am going to find this number. So I'm going to see, okay, what atom am I looking at? And I'm like, the arrow's pointing to a carbon. So I come here, look at my periodic table. Okay, so that means carbon has 4 valence electrons. Now I need to subtract how many electrons that carbon atom owns. So I'm going to come over here. Well, I'm going to actually erase this. And I'm going to draw it out so we can visually get an understanding of what's going on here. All right. Like this. Now, if I take a look at this central carbon, these sigma bonds or covalent bonds, they just are representing like this, right? So this molecule right here is this molecule. Now we are going to say, when we look at this molecule here, because these are covalent bonds, that means it shares electrons. So when we look at these two, okay, they're sharing. So carbon's only going to worry about this one. There's two here. Carbon's only going to worry about this one over here. So it's only sharing half of the electrons in those bonds. So I'm going to circle the electrons carbon owns. It only owns 4 of them. 4 of the 8. So those electrons there, I minus. And then that's going to equal the formal charge. So this is the formal charge. So 4 minus 4 is 0, which means it's neutral. So the formal charge for this carbon is 0. And when the formal charge is 0 or neutral, we just don't write it down. It's just completely neutral. Now, if we take a look at this carbocation, we are going to have to erase this guy. We're going to have to put in the formal charge. And so that means this guy no longer exists. And so now, this green force, it's the same all across the board, because the first number in this calculation is how many valency electrons does the carbon atom supposed to have. So we're looking at this carbon here. We go to our periodic table. We see that it's a carbon. We don't care what the formal charge is. Just ignore that for right now. How many valency electrons does the carbon atom have? 4. That's that number. Minus how many electrons it has around it or owns. So this is what it looks like. We can then translate this Lewis structure into this if we'd like. And we can see that there's 1, 2, 3 electrons. So we are going to erase this guy and go 3. So 4 minus 3 is a positive 1. So you could go just a plus, that means positive 1. Or if you want to do a little bit more work, you could go plus 1. But really, now that I'm thinking about it, you don't do it that way. That's just not how it's really done. Drawing that plus tells us it's a plus 1 charge. All right? Now, if we do the same process here with this anion, what do we have here? We have a carbon, okay? This is a minus 1, so that means it has a lone pair. And so that lone pair is going to be right here. So we can just go, that's a carbon atom. How many valency electrons does that central carbon have? 4. How many electrons does it have around the central carbon? 1, 2, 3, 4, 5. 4 minus 5 is a negative 1. That's why we have our negative charge there. So you can see that's how you do it. That takes a little bit more time drawing out all the structures. And so there's just a quicker way to do this. And the way I do it is when I look at the structure, I write down how many valency electrons it's supposed to have, minus, and then I count how many bonds. There's 1, 2, 3, 4. So I know that carbon is neutral. When I take a look at this guy, I know it's 4 valency electrons minus how many bonds? 1, 2, 3 equals plus 1. Now this one, it is 4 valency electrons minus, and this is how I count it. Count the bonds. 1, 2, 3, and any lone pair you count both electrons. So let's do this again. Let's look up bonds. 1, 2, 3, 4, 5. And that would be equal a -1. So you count the electrons, the lone pairs, and then you count bonds. And I know that may be different than what you were taught in general chemistry. In general chemistry, you had a formula that you type in or enter in the information to figure out your formal charges. If that works for you, use it. That is great. I've just come up with this method because it just goes fast for me. All right. So with that, let's apply this principle to something else other than carbon. So let's draw an alkoxide. Well, something that looks like this. What I want to figure out is what is the formal charge of this oxygen atom? When I go to the periodic table, I see it's in group 16. So that means this oxygen atom has or should have 6 valence electrons. And now using my trick, you count how many bonds and how many electrons that are in lone pairs. So I have 1, 2, 3, 4, 5, 6, 7 equals a -1. So the formal charge on this oxygen atom is a -1. What would the formal charge be on this ether? Well, I see an oxygen atom, so it has to have 6 valence electrons minus 1 bond, 2 bond, 3, 4, 5, 6 equals 0. So that is a neutral oxygen. And we already know that's neutral. Why? Because of the HONK rule. If oxygen has 2 bonds, it's neutral, and it has 2 lone pairs. All right. So looking at, let's take a look at a nitrogen species real quick. Oh, no, let's talk about this for a little bit. So you will see structures, okay, like this. I could draw a structure just like this on the exam or practice homework, and you should know, that this oxygen only has 1 covalent bond, 3 lone pairs. That has to be -1 charge. I may not draw in the formal charge. If you can see that I'm drawing in the lone pairs, then you already know what the formal charge should be. If I draw the same structure like this, do you see how I'm omitting the lone pairs? But I gave you the formal charge. And so that formal charge of -1 is going to tell you that there are 3 lone pairs, even though I may not draw them in. So if I take another species like, let's see here. Let's draw a amine here. I draw it just like that. What is the formal charge of that amine? What does the HONK rule tell us? And if you're somewhat like me, you just have to write it out for some reason. The HONK 1, 2, 3, 4 rule. Okay, so that means nitrogen has to have 3 bonds. Okay, so that doesn't have 3 bonds. So right off the bat, I know that is not neutral because that rule is broken. So now I just got to go to my book, find out what group number nitrogen is in. And nitrogen is in group 15. So that means there has to be 5 valence electrons. And I see this nitrogen. How many bonds? 1, 2, 3, 4, 5, 6. So that nitrogen right there has to have a formal charge of -1. Or when they're ones, you never put in the number. That's a -1. Okay. What if you had a nitrogen with 4 bonds attached? What would you think? Same rule. 5 minus 1, 2, 3, 4. 1. So that would be a +1 amine. Okay, let me just reiterate and emphasize how important it is to know how to do formal charges. It's going to help you know reactivity and predict reactivity. It will help you understand if the reaction is even probable. Very, very important. So a challenge that we have as organic chemists, it's a minor challenge, but it's the fact that when we attempt to draw molecules on a 2-dimensional plane of glass or a chalkboard, we have to understand that molecules are not 2-dimensional. But a lot of molecules, not all, a lot of molecules, they're not flat. They have 3-dimensional shape to them. And so we need to devise a way to draw a molecule on a board, but still represent that 3-dimensional shape that a molecule has. So remember that a carbon with 4 bonds isn't just a carbon with 4 bonds in the same plane and flat, but it is tetrahedral. Remember in general chemistry that we have tetrahedral shapes. And so to represent that tetrahedral shape, we also have to understand that, look, the way I drew this, what is the bond angle the way I drew it? That is 90 degrees. But a tetrahedral molecule does not have bonds that are 90 degrees from one another. It's 109.5 degrees. And so what we have to do here is represent that actual angle. The way that we demonstrate the tetrahedral geometry of that molecule is by using wedges and dashes. So now do you see how that bond angle there is greater than 90 degrees? And we want to represent it as 109.5. Because this is tetrahedral, one of these bonds is going to be a wedge, and the other is going to be a dash. And so what this is telling us is that this wedged bond is coming out of the plane or out of the board at you. So if I'm looking at this molecule, these 2 bonds right here are in the plane of the board or the plane of the glass. And this bond right here is sticking directly out of the glass. And then this dashed bond is pointing in the opposite direction of the wedge, going out of the board in that direction. So what we're going to have to be able to do is get your hands on a modeling kit And you're going to see when you build this molecule with your modeling kit that one bond is going to be pointing out of the board and the dash is going to be pointing into the board. And so that's how we represent the bonds in tetrahedral carbons, these wedges and these dashes. Now when we take a look at a zigzag structure like this, so that's a pretty good zigzag structure. Now I want you to contrast this zigzag structure to this one in blue. And one more. You clearly see a difference, right? Now, why is the blue one down here wrong and this one up here correct? Well, it has to do with this bond angle right there. You are trying the best that you can to represent that 109.5 degrees. Here, that angle between there, clearly not 109.5. So this zigzag structure is incorrect and will result in loss of points if you're going to draw zigzag structures like this. You need to have that beautiful 109.5 bond angle. And that's why we draw zigzag structures. We're representing this angle. And so then when we have a zigzag structure, how do we represent the wedges and the dashes? Well, the wedges and the dashes are quite simple here. We see, let's number the carbons. 1, 2, 3. Now when you take a look at carbon 2, do you see how its apex pointing up? And then when you look at carbon 3, the apex is pointing down. So you're going to find that apex and you simply draw a wedge and a dash like that. You do not, if I'm calling this carbon 2, that's carbon 1, carbon 3. If this one right here is carbon 2, you do not draw the wedges and dashes like that. This is a no-no. Don't do that. You find the apex and you draw the wedge and the dash. Now students may ask, and it's a very valid question, if this is carbon 2, is there a difference between that? So we have a molecule on my left, a molecule on my right. Is there a difference between those two? And the answer is no, there's no difference whatsoever. Why? Because this wedge right here is saying it's coming out. This wedge, almost knocked my book over here. This wedge is saying the exact same. It's coming right out. This dash is saying it's going into the board. This dash is going into the board. So what you can say is that if you trace the green skeletal backbone here, these blue bonds are just perpendicular to the green bonds. The green bonds are in the plane of the glass, and these blue bonds are out of the plane. So it's kind of the way I look at it is if I could take my eyeball and look down this green backbone. So I'm just like looking at it. And I'm just looking and I can see the green backbone right through the plane. And then I see these bonds right here. They're outside of the plane. So it's kind of like looking if right down the center of my chest, if that's the green backbone, the blue bonds right here are on either side of that green backbone. Kind of like handlebars on a bike. So those, if I leave these wedges drawn as is, what do I have here? I have a methyl group and a methyl group. If I want those to be hydrogens, I'm going to have to draw them in when you draw your wedges and your dashes. So if you ever just draw a wedge like that, that's legit. But there is a methyl group. Do I have to draw in the dashed hydrogen? No, I don't. If I don't want to draw in my hydrogens, I don't have to because we are organic chemists. So that is a valid wedge. Yeah, so if you're only going to draw one wedge or one dash, it can go right in the middle like that. But the moment you have to put two groups on that carbon, let's look at this one, you have to put a wedge and a dash. They have to be opposite. There's the wedge, there's the dash. You can see, why do I want it like that? Because I'm looking for, whoa, that 109.5. So that 109.5 angle is for every single one. That's why we draw the zigzag. That is why we draw the wedges and dashes. All right. Another thing students do that's kind of a pain and not actually correct is they draw something like this. They'll have their zigzag and they'll draw a wedge there and a dash down like that. Incorrect. Don't do it. You find the apex. I'm going to say it one more time. I know I'm now a broken record. If we're looking at this carbon right here, we put the apex is pointing down, so that means the wedge comes here and the dash goes like that. And then you put in what elements there are. If that's a hydrogen, put in a hydrogen. If that's a chlorine, put in a chlorine. All right. Now, as we progress through the course, we're going to be able to look at cyclohexane rings. And even on a ring, you can have a wedge and a dash. And we're going to look at all different sorts of structures. Okay? Your book talks about those early on. I'm not going to spend too much time on that right here, but you could read about it and looking at all the different ways we can draw molecules. But this wedges and dashes to represent tetrahedral carbons is super, super important. Okay. So looking at the time, I'm going to stop here. So the next topic that we're going to take a look at is another topic that you learned in general chemistry. It's called resonance, and you need to review that. I'm going to go through the basic rules of it again, but it's something that is so important for your success in organic chemistry, because resonance structures are going to be a thing from here until the end of Orgo 2, and it's going to go into biochemistry. It is a principle that never goes away. You cannot approach this, hey, let's learn the bare minimum just so I can pass the test, and think you're going to be okay, because you're not. You have to understand this to be successful in the future topics and in Orgo 2. And so if you find this a difficult topic, you're right. Resonance structures a lot of students struggle with it because it's so new and it's just what it is. But I just want to make you aware that it's so important that if you're finding yourself struggling with it, you need to get the help that you need. So look to the TAs, office hours, anything just to get this down pat. It's super important. Okay? So let me know if you guys need anything and need any help.